Hello, welcome to the lecture Electron Spin Resonance Spectroscopy or ESR Spectroscopy. In the previous lectures through NMR spectroscopy, we were dealt with nuclear spin. Here I am discussing about electron spin related spectroscopy, which is ESR spectroscopy. It is also referred to as electron paramagnetic resonance spectroscopy, where we are considering unpaired electrons, compounds containing unpaired electrons. This is a very relevant analytical technique based on absorption of microwave radiation in presence of an applied magnetic field by paramagnetic species. Where would see unpaired electrons? Here, hydrogen atom, oxygen, NO, Na2, etc. having unpaired electrons. Here, the oxygen atom, although it's a stable molecule, it has 16 electrons, of which there are 2 unpaired electrons in a degenerate pair of molecular orbitals, a pi star orbital. So it is paramagnetic. Then radicals, carbons, all are having unpaired electrons. Then transition metal ions, which may contain 1 to 5 unpaired electrons in their d orbitals. So it has different applications in fields such as organic reaction mechanisms, in metal complex studies, and in biological fields. Next, we are moving to the theory of ESR spectra. As we dealt in the introductory lecture of resonance spectroscopy, the degenerate electron spin levels undergo Siemens splitting in the presence of an external magnetic field with an energy gap of minus half and plus half, with energy gap GS, BSBZ, where beta S is the Bohr magneton, GS is the electron G factor, BZ is the applied magnetic field. That is, if a light in the microwave frequency falls on the system, the electron flips or undergo transition towards the upper level, and the frequency will be delta E by H. G can be GS, beta S, BZ by H. Again, here we are dealing with single electron. For single electron, there is only one transition, and we have one spectral line in the ESR spectrum. Generally, we are getting a broad spectral line in ESR spectrum. So it is difficult to locate the exact peak position. Because of this, what we have to do is that we should draw derivative plots. That is, for this broad ESR spectrum, as it is difficult to get the exact position, I am going to draw its derivative plot. That is, we can see here is the x-axis and this is the y-axis. And if we take slope, that is dy by dz, this part has the positive slope, and this part has the negative slope, and for this part there will be the slope is 0. So if we plot dy by dx against x, if you are plotting the slope against x, the graph should be like this. That is, the line we pass through, and there is a positive slope and a negative slope with a 0 point. And this point where the value of dy by dx is 0, which gives the exact position of the peak. So in ESR, we are always taking derivative plots to locate the exact position of peak to get the exact frequency. Next, we are interpreting the ESR spectrum of hydrogen atom. We know as it is simple, ESR spectrum of hydrogen atoms must be simple as it contains only one electron, and we would expect only one ESR line, but the experimental studies shows two equally spaced lines in the ESR spectrum of hydrogen atoms. How this happened? That is like NMR can be explained in terms of interaction between electron spin and nuclear spin, and this interaction has been termed as hyperfine interaction. Thus, hyperfine interaction occurs as a result of the magnetic interaction between the electron spin S and the nuclear spin I. The hyperfine interaction in ESR spectra is analogous to the fine structure, that is, nuclear spin-spin interaction in NMR spectra. As a result of this interaction, the ESR peaks are split into several lines. In the case of hydrogen, here the strength of interaction is represented by the parameter A, which is called hyperfine coupling constant. Hyperfine coupling constant. Next, let us consider the hyperfine interaction of hydrogen atom. Hydrogen atom, as we all know, it contains one unpaired electron with H is equal to plus or minus half. Degenerate levels. A proton with, here there is a proton with spin half and a nuclear spin of I half. In a proton there must be a nucleus, a proton and an electron. Thus, MS plus or minus half, and there should also be an Mi with plus or minus half. In the absence of magnetic field, the electron spin energy level are degenerate, that is having the same energy. Application of magnetic field removes the degeneracy, the MS minus sublevel going down and the MS plus half sublevel going up. Each of these electron sublevels interacts with the nucleus, giving 4 sublevels designated by the value of Mi, that is minus half. You should note that here the electron and nucleus, you should write positive. If you are, this is positive, this your ground will be negative. So since it is two equal opposite charges, and give 4 energy levels. This is hyperfine interaction. Now we have 4 energy levels. So we can expect 4 different transitions from each ground state to the 2 excited states. But here also we can find only 2 lines. How this happens? Here we have to focus on selection rule for ESR transition, which states that the value of Mi should not change. This selection rule may be interpreted by saying that the nuclear motion is much slower than electronic motion, so that during the time electron changes its spin orientation, the nucleus, being heavier, has no time to reorient its spin, so that delta Mi equal to 0. So, the spectrum will contain 2 lines with intensity ratio 1:1, that is doublet. Next, I will move on to the hyperfine spectrum of methyl radical. Methyl radical, it contains an unpaired electron with S is equal to half and 3 equivalent protons. Since for a proton I equal to half, it is evident that for 3 equivalent protons, nuclear spin must be 3 into half, that is 3 by 2, and it should vary from minus mi to plus mi, which is minus 3 by 2, that plus 1, minus 1 by 2, that plus 1, plus 1 by 2, that plus 1, plus 3 by 2. Hence, each of the electron spin levels can be divided into 4 sublevels by the hyperfine interaction. And obeying the selection rule, we have only 4 lines, that is, keeping delta mi 0, you can have 4 lines with intensity ratio 1:3:3:1. This is the hyperfine spectrum of methyl radical. All the observations are consistent with 2Ni plus 1 rule. Here, I equal to half for E. That since it is only the radical, I equal to half. Then, so 2Ni plus 1 becomes N plus 1. So for ESR, here is to follow the N plus 1 rule. That is, if there are N nuclei with spin half, there will be N plus 1 hyperfine line. So, for methyl radical, there is 3 protons, hence 4 lines. Then we can have different radicals. Consider benzene radical, C6H6 radical. For them, the number of signals will be 6 plus 1, 7. For phenyl radical, that is C6H5 radical, number of signals how many? 5 plus 1, which is 6. And for cyclohexatrienyl radical, this is the structure. Here we have 2 CH high protons, but one is withdrawn and give it as a radical. And all other positions have 1 hydrogen each. So total there is 7 hydrogens. 1, 2, 3, 4, 5, 6, and this 7. And the number of signals we are expecting 8. Thus, ESR can be considered as a fingerprint that helps to identify the free radicals present in a sample. Here, I am concluding this lecture, the basics of ESR spectroscopy, and it is sufficient for you. Thank you, my dear students.